Hey there, this is the video on volumes by cross-sections. And in this video, we'll be looking at, developing a method to compute volumes of three-dimensional objects. That's very, very similar to the way in which we computed areas using Riemann sums in the previous chapter. And hence we will see how integrals play a part in here as well when we move on to compute these volumes for three-dimensional things. And just as a first example here, you probably remember the formula for the volume of a sphere with radius r. Right, so the formula here is volume equals 4/3 times pi times r cubed. And what I'm going to try to do in this video is, prove this formula, right? Show you why it's 4/3 pi r cubed. And the way that I'll do that is, again, essentially the same as what we did for deriving the definite integral. If you look at the image here, right, if you can imagine, if you have a sphere in your hand, like a ball of some sort, and you have a very sharp knife, and you just slice off, right, a portion of the sphere, exposing this circular region here, right? That's called a cross-section of the sphere. Technically speaking, it's an intersection of this three-dimensional object with a plane, right? And if your plane is perpendicular to the x-axis, right, so this is what it will look like, this cross-section right here. And if you remember, for computing the areas of regions under a curve, we did them using rectangles at the beginning and used this as an approximation. But as the number of rectangles grew larger, then we were able to get the exact value of the area by pretty much considering the area as, the accumulation of infinitely many, infinitely thin line segments. And in fact, that's what's going to happen here for volumes, where we're going to consider this spherical shape, right, this ball, to be an accumulation of infinitely many and infinitely thin slices that are all circles individually. And by combining all these circles up, you're going to get this volume, right? And so this is what it looks like for area. Right? Here you have your Riemann sums. Maybe n is, 20 here, maybe. In the second picture, maybe n is, I don't know how many this is. Let's just say 60. And once you get to the exact area, now it's an integral. Right? So n has gone to infinity. And now you have, again, you can think of this as infinitely many line segments that are infinitely thin, of which the accumulation gives you the exact area. So what does that look like for our sphere here? Well, for the Riemann sum approximation for the area, what did the terms look like? Well, remember the term was the area of the ith rectangle, right? And the sigma notation says add all of them up from I equals 1 to 20 or I equals 1 to 60 or whatever. And to get the area of the rectangle, we just needed to compute width times height, where the width was delta x, right? This was a uniform subdivision, right? So a to b, the whole interval, is divided into n equal width subintervals. And the height of each rectangle is given by this fxi star term, right? If this is f of x, right, that's a curve y equals f of x. Then you pick an xi star from each subinterval, and that tells you what the height of the rectangle is that you're making. And so we want to do the same thing for our sphere, right? What will the approximation look like here? Well, well, it's not going to be a rectangle anymore, right? It's going to look something like this, where it's a coarser representation of getting all these cross sections that are infinitely thin, right? Where instead of that, now we have these cylindrical sections. And I can't draw this properly, so I'm not going to do that. But now they're cylindrical cross sections. Cylinder. And so the idea here is that we can also approximate the volume of the sphere by adding up the volumes of all these cylinders. What we'd like to happen here is, if on the right you have your summation, right? N is the number of cylinders, so here you have, I don't know, maybe 10. And now you're adding up the volumes of these cylinders by letting the number on top here, n, go to infinity. Again, well, what we're going to get is this, which is the exact volume of the sphere. So now our question is, can we get a general formula for the volume of the ith cylinder? All right. So say I ask you, what's the volume of this particular cylinder here, right? Well, it turns out cylinders are easy to work with, right? A cylinder, well, technically a cylinder is anything that looks like this, where you can have a region and then it's just really translated vertically to produce this three-dimensional solid. And the volume of this, if the base has area A, the volume is just A times H. Area of the base times height. For these cylinders, they're also what we call circular cylinders, where the base is circle, right? So here you get your standard formula, pi r squared h, where pi r squared is the area of the base. The issue is now that r is varying, right, from cylinder to cylinder, much like the height here was changing from rectangle to rectangle, right? So the height depends on x. Here the radius depends on r, which varies with x. And so before we get to all of that, let's look at the general method first. Again, cylinders, you can compute volumes using this formula, area of the base times height, where you're fixing the base to be at a specific point xi star. And so the Riemann sum you're getting here looks like this. Summation from I equals 1 to n of a of xi star times delta x. And when you let n go to infinity, well, what is this? Right? By definition, this is just the integral of a of x dx from a to b. Right? Again, we're assuming here that delta x is b minus a over n, where a and b are the left and right endpoints. Right? And so this is pretty nice here, right? Because what this tells me is, in order to compute the volume of any solid where I know exactly a formula a of x for what the cross-sectional area is when I slice perpendicular to the x-axis. Right? So if I know this a of x function, what is my area at any given x? Then I can accumulate all these infinitely many areas up and get the volume of my solid. Right? And it doesn't just work for spheres. You can have maybe a square pyramid that looks like that. It's on its side because I want it to be or I wanted to have cross sections perpendicular to the x-axis, right? So you can think of it like x-axis here. And so now when I slice the square pyramid at a specific x-coordinate, I'm going to get a square as the cross-section, right? And this will also give me a formula a of x for any given x, right? So if I pick x to be at 0, for instance, I'm going to get a larger square. As long as I know this a of x function, right, what the cross-section is in general, then I know the volume, right? I can just take the integral of that area function. And so applying it to, again, back to our sphere example, what is the cross-sectional area, right? We know that the volume is equal to integral of a of x dx. X ranges from a to b. Well, okay, so it's a sphere with radius r. Let's assume that its center is at the origin, just to make computation simpler. Then your x-coordinate varies between minus r and plus r. Right, so that's your upper and lower limit, r and minus r here. And for each x-coordinate, right, I can slice it as, or I can slice it as at minus r over 2, for instance, or r over 2, or 1/3 r, or exactly at 0. And what I want is a general formula a of x. Now, I know that the cross-section is a circle, right? We've talked about this. So the area function with respect to x is just pi times the radius squared. But what is the radius? So if you look at this particular cross-section here in the image, if this is the x-coordinate, well, x, the radius is given by this height, right? Again, we're talking about the radius of the circle here and not the radius of the sphere, so don't confuse them. But how do I find this radius? Well, look at the arrow here, right? They're already telling you it's the y-coordinate of whatever this point is on top. So if I know what the y-coordinate is, I know what the radius is. Therefore, I know what the area function is. So now the question is, what is this curve on top? Right? What's my y-coordinate? Well, now that curve, that's just a semicircle, right? Of radius r and centered at the origin. So this is the curve y equals square root of r squared minus x squared. Again, coming from the more standard form of the circle, x squared plus y squared equals r squared. So, at my cross-section, with x-coordinate, I'm just going to use x here, the radius of my circle, of the circular cross-section, is the square root of r squared minus x squared. Therefore, the volume of the sphere is I just need to integrate from the leftmost x-coordinate to the rightmost x-coordinate, so minus r to r, of all these, again, circular areas. So it's pi r squared, which is r squared minus x squared squared, and then dx. This is now equal to, well, now it's just simplify. This is just r squared minus x squared dx. This should be the pi r squared minus pi x squared. Right? I mean, you can do this yourselves. But what you'll get here is eventually what you'd expect. So r is a constant, right? So it's pi r squared x, and then minus pi x cubed over 3. And you're evaluating everything from r to minus r. And yeah, it's easy to check here that you will get the formula for the volume of the sphere.